we have a few things to do today, on the lecture, but most of it is familiar. Who have heard of Excuse Magic? Cool. The new thing you learned today. All right. Okay, now this doesn't want to work. Okay, pen work. Okay, 89%. Good. All right, you're good. So today's learning objectives are rigid body and computational space and coordinate system. So that's why I think you know most of them, and vector algebra overview. I'm going to lightly overview and tell you what you have to go and perhaps just study or review yourself. I think most of you know the 3 Bool and 1 Round website on his YouTube channel. I think it's one of the best mathematical everything explained. Please don't be late. Everything is explained very clearly with lots of good examples that visualize what the concept means. All right, because math is very cut and dry in my opinion, but they made it fun. I want you to check these or ask yourself, am I doing cross product and do I know what is the concept? Can I do 2 matrices without using my calculator? If the answer is yes, you don't have. If the answer is no, definitely review that. Just watch it. I posted these also in today's lecture page, so you can access through there as well. So the rigid body is a physical object. A rigid body is a physical object which the distance of 2 points remains the same no matter how the object moves. So if you assume my pen, is this a rigid body or not? Yes, because if you assume these 2 points, the tip and the end, and then you start moving, these 2 keep the distance from each other. I don't think it's the door, I think something outside, right? All right. Who planned this? All right. So bring an example that is not a rigid body. Like, is my phone a rigid body? Yeah. So what's the example of non-rigid body? Water. Why?
Because it flows at 2 points water.
Okay. So that example was liquid. How about a solid? A jump rope. Jump rope. Well, no, because the length is the same, right? When I said distance, I mean the length. The length. And do you remember about when you were talking about arm and then you said tendon? Your tendon length changes when you move, right? That is not a rigid body. What else?
Oh, I was thinking like that, it kind of like scratches out.
So, why do we care if something is rigid body or not? There's one main reason. We have set of equations that we use for rigid body. We cannot use them for non-rigid body, but they have their own equations and physics. For now, in this course, we only focus on rigid body. So if you pick 2 points on something and you create a vector, that's good enough to follow the velocity, position, anything. All right, so you don't have to worry what if these two changes affect each other. That's a new set of problem, right? You don't have that problem. So that's the only thing that you want to focus. And it's a lot easier to deal with rigid body. Now, a robot consists of 1 or more rigid bodies that they're called link. And they are mechanically connected to each other through, remember, a joint connects, so basically connects to the body. Ground always counts as a link. It's just, let's say link 0, common ground. So things are connected. Now, why is this important? right? So if you have a robot that is connected to the ground, so the robot cannot move with respect to the ground, and you want to find the end effector position, your reference point is the ground, and that's not going to move. So you can find the kinematic and dynamic of the end effector and you're fine. But let's say this was a moving car. It was doing its own thing and the car was also moving. It kind of changes your problem, right? It makes the dynamic a little more complicated. Again, another set of equation will come in. You can solve it, but we're going to simplify our problem. So we're going to concentrate on non-moving robots in terms of they're always connected to the ground. All right. At some point, when we work with cartwheels for control and trajectory tracking, then we might use moving objects. All right. Now, everybody knows the Spot Mini, right? So let's check what is a link, what is a joint. So let's see, these green dots, if they represent joints, I didn't show all of them, I just showed majority of them. Then these purple ones are the links. So you see that the joint is connecting to link always at all times. All right. It's very annoying. Okay. Friday be fine. All right. So there are a few definitions about configuration space. I think it's a good idea to understand what they are. I don't want you to remember like verbatim, like one word by word. What I will never say, okay, right, what is configuration? But I want you to understand what it is. All right. So first one is, what is a configuration? Because I think I've said configuration so many times so far. So so it's a complete specification of position, okay, of every point of robot. We said our robots are rigid body, right? So if we have a specification of those points, then we can describe the geometry of our robot. It's not about dynamic, it's just what the robot is, right? So if you want to describe someone 6 foot tall, I don't know, wide build, or I don't know, these are the configuration, right? Or the specification. So basically where the joints are, how long the links are, how many links is there, how they're connected. So these are the configuration of your robot. Now state, I put manipulator here because we are focusing on robot manipulator. So robotic arm, legs, anything that has links and joints. There are a set of variables that describes the manipulator dynamic and future inputs. So if you have those, you can tell based on the time what will happen. This is like state of everything. So if you have the initial condition, if you know how the system is connected, and you know the dynamic, you can tell where the system will be in the future. That's the state of the system. Now, state space is all the possible states. Now, for manipulators, you need a few things to be able to estimate the future of the robot, where the robot is going to be. When I said the robot, the end effector, the specific joint or link. It that set contains two things. One of a position, one of a velocity. Position, again, remember, depending on the joint, either revolution or if you have prismatic, it's a position that changes along the line. Do you remember joint variable that we discussed on Wednesday? So joint variable plus joint velocities are your state space for manipulator. Because if you know what kind of link you have, how much your joint is changing, it is revolute, let's say angle, it is prismatic, how much it changes along the axis. If you know what velocity is to change, you can tell where the robot is at any time. Why? The links are rigid body, they are fixed. They're not going to change. So if you know the other information, you can just use sine cosine of that length, and then find out where and the factor, for example, is that. This is basically kinematic. We're going to do this exact procedure to find a position of our index, right? So Joule variable and Joule velocity are very important. And at the beginning, every robot you see, every schematic, try to find out. Okay, but let me see if I can find what is the Joule variable and what's the Joule velocity. Okay, we will be well versed in figuring that out. Configuration space, or C space, is the space that contains all the possible configurations. Now, what does that mean? Let's say that you have, let's do here. So let's say you have a robot arm, has one joint and one length, and this is theta 1. What is Q here? I'm going to form a state variable. So joint variable, what's joint variable? Theta 1. What's joint velocity? I'm going to show you Q dot. Theta dot 1. So state space is going to be theta 1, theta dot 1. If you look at literature, that's the first thing they define. This is my system. These are the state space. So you want to know what are your variable, what is that you're changing. Every time you simulate, those are the variable that get initial condition. And then you want to know when they end up. Yes. No, it's S that is saved. Yeah, my S and delta. Good news is I already did the annotation part, and I've written my best of ability. So it should be more clear. Now, for configuration space, let's say your robot looks like this. So by robot, manipulator arm. So if this is your ground, this is theta 1, this is theta 2. So your state is going to be different, right? But then the configuration space is, what if this robot moves? And this is not a configuration, right? Because that's just two linear can move. What if it was here? What if it was here? You still have the same joint variable, but your configuration is different. Now, C space is all these configurations for that robot. Okay. Sometimes, because of the constraint of the joint or the system, you might lose some of these possible configuration, right? Let's say one of the joints only moves 0 to 90. So you cannot reach all of them. That you won't have the possible configuration if the joint, which is a silver motor or cell motor or whatever, instead of 0 to 90 has 0 to 180, right? So the constraint of the system is going to affect it. But for that system, all the possible configuration will be your configuration space. The other thing we need to know is degree of freedom. I think that everybody always knows what it is, right? So the minimum number of real valued coordinate that we need to describe our system or represent that configuration. Like in 3D space, if an object is suspended, how many degrees of freedom? Think of airplane. How many degrees of freedom in airplane? 6. It's all 6. Pitch, roll, yaw, up, down, and then this way. Right? So every object that is in 3D space and suspended, there's no constraint on it, you're going to have 6 degrees of freedom. Now, if a system has more than 6 degrees of freedom, which you will see, it's redundant. It's not a bad thing. It's good. It's going to help us. Human body has more than 6 degrees of freedom. It's a good thing because it gives us capability to do different tasks and move our body in different ways, but we're still in 3D space. All right. Let's see some. Okay, let's do this one and let's see some example of degree of freedom. Robot workspace. So these are kind of connected. So now we saw the configuration space, right? Now, can everybody see this projector? Right? So the workspace, this is
has the projected the redirect. But the whole system was designed based on the functionality of this guy, for this type to be. Right? So you could have different designs for this that does the same thing, same configuration. Now, the workspace of this guy is, if you imagine there is a tracker on this end effector, all the possible motions you move right here, all of these is going to create the workspace where this can exist. Now, this space is limited 90 degrees. This one is 180. Here is 180. This one is 270. All right, so three different joints, three different constraints on their motion, all right, will create all the possibilities that the designer is this lamp to point.
So this gray area for this two, first of all, how many joints this robot has? Huh? 2? So theta 1, theta 2. So this is the joint. Remember, we'll show the arrow to show how it moves. So this is your end effector. Your end effector is going to be placed here, whatever it is. I'm just going to put a fork here. The gray area is all the possible places this fork can go. Okay, so the system was designed to do this. You can design a different system that does the same thing. I want you to see the difference here. No, the base here is fixed. So you don't see that. If it was, they would be going this way, or they would show this. That's exactly why you have to always mark. If there's a joint somewhere, you have to mark, and the easiest way is to show an arrow that shows the direction of the movement. No, that's the top view. That's the, so when you see from here, this guy and this guy. So this one also moves. All right. Don't confuse everyone. Does everybody see the different, that this is not, there's no joint here? Because if you see from top here, I'm gonna look at top. So there is this box, which is this guy, this link. It's welded to the base. But because you still see this joint, you see that circle. So usually the revolution is shown by a circle, there's a dot in it, there's an arrow, so remember the revolution. So when you are analyzing, designing, you want to make sure that your audience or reader exactly know what you meant. So it could have been even better if I would show, I'll probably do this. Or on the side, if you're a mechanical engineer, I think you do this to show value, right? But they're probably like, okay, you probably know what to provide. This is taken from part of a book. So this has two variables, theta 1, theta 2, right? And the gray area is our workspace. So all the possible motion of your end effector. Now, let's practice the state space. What's the state space of this robotic manipulator? Let's see. Anybody wants to volunteer? No, I'm volunteering. You don't volunteer. So what's the state space and how do you find that for this robot? So that's 2. How many in this set of state space for this robot? 4. So what are the other 2? The 2 of them are correct. Right. So always the joint variable and the joint variable, but that velocity, right? So theta 1, theta 2, theta 1, theta 2. So get used to every time you see steps, find out what's the state space. All right. Here, that's excellent practice.
Question on the state space, the order matter there?
Well,
Theta one.
this is
theta
like a
one.
convention. You want to start, so let's say if you have x on x dot, because that one is the derivative of the other one, you want to introduce this, the first state and then the derivative of that, right? So we usually say yes, theta one, theta two. So position first and then the sequence, velocity sequence. If you had acceleration, then you would have acceleration sequence, right? Thankfully, we don't have acceleration. Thank God. Gonna be very complicated. Now, let's practice for number 8. So all the gray areas showing the workspace of these robots, the different robots we saw on Wednesday. All right. So you see that depending on what kind of drone they have and what configuration they have, their workspace is different. So if you see C and B both have a revolute, prismatic, but they have two different workspaces because how they are configured. Right? Now, for A, what is the state space? Write down or walk around check. What is the state space? They're the same thing. No. So these are. So one right state space. Yeah. Okay. How about you? What is R? So try to use the, if you set for prismatic, we're gonna also DI, use D for prismatic and theta for revolute. Right. There, right. Oh my God. It's the point thing. The first one is variable one, variable two, is the third variable one. Right. All right, so whenever I ask you to do something in a class, it's kind of first helping you to see if you realize or understood what we talked about. 2, if you're picking it up, because 3, I won't talk as much, you do something. So don't sit down and wait for me to go and see if you're doing it. Okay, it's your time to think and not be just talk to, you know. Yes. Oh, okay. Feels like this is no problem. Yeah. Prismatic. Wherever the plate is.
Yeah.
And then the film is-
I like how you say.
Yeah.
Okay.
As you can see, also the workspace is showing. Great question. I'm gonna talk about that. All right. So you can do for all 4 of them. I'm gonna do for 1. So that the other 3 are when you're studying or you just want to check. So here, so since there is no arrow, I'm gonna we are always follow right hand rule. So we're gonna turn counterclockwise. I didn't tell you, but it's not important for now. So go on. And here, so we said that if there is a so this is this one theta 2 is shown in 3D. So if there is that handle, means that you're rotating that handle along the axis, so it's rotating this way. And then for prismatic box shows which direction, which side of the box you're moving. So it's this direction. Now it could be, now these three motions will create this workspace. Now, your robot can do this all at the same time, or it has to be doing it one by one. We don't know, we don't care right now. But it will reach in at any point in this gray box, yes. We will get there, don't worry. But whenever there's a handle, you know that that wing is moving. Okay, for now, think of that. So we will get there, all right? It's next week. I don't want to confuse you because that's the beginning of kinematic, all right? So now, state space is going to be the joint variables, theta 1, theta 2, and this is prismatic. This is the third joint, so I'm gonna say D3. I'm not gonna say D1 because I want to show the sequence. So if I say theta 1, theta 2, D3, and this is theta dot 1, theta dot 2, D dot 3, if I just showed you the state space of a robot and ask you, can you draw a configuration? You can draw something that resembles really well or close to this robot because you don't know the directions yet, but you know there is a revolute, then there's another revolute, then there's a prismatic. But if I say theta 1, theta 2, D1, you'll say, is D1 first and then theta 1 start, or is it the way that you wrote? So these are conventions to make our life easier. All right. Do the others for yourself. Yes. Yes, so these robots, based on their constraint, that's their workspace. No. So you need to know what kind of joints you have, what are their constraints, meaning 0 to 90, 180. And then you basically draw all the points and can give you the workspace. All right. So when you're designing something, it's backward, right? You ask first, where does this robot need to reach? And then what other capabilities does this robot has to have? And I'm going to design what it's going to look like. And you can have different designs for that. All right. So we talked about degree of freedom for space, for objects, suspended object in 3D space. So this is an object. I'm going to move around. So this is yaw, right? Yaw, roll, pitch, depending on whose definition you're following, and I broke it. And then you can go forward, backward, up and down. Now, are all 3D objects, all objects in 3D space have 6 degrees of freedom? Can you bring an example? I'll give you an example. Who plays VR? All right, let's say we all play VR. We're all rich and we can afford it. So when you place a headset on your head, let's say someone told you have to stay, sometimes they tell you that the walls are so close, you have to put your feet on the footstep, you have to just stay there, you can't even go up and down, right? Your head can only move. How many degrees of freedom now you have? 3. You can only do the rotations, right? Roll, pitch, yaw. Now, let's say in another scenario, another game that is more developed, you can actually move back and forth, up and down, right? And still move your head. So if you imagine that point of reference is your eye, because you're seeing things, your eye is rotating, goes up and down, and moves in different directions. Now how many degrees of freedom you have? Now you have space. So we have to look at the constraints when we are deciding about degree of freedom. Degree of freedom is like the minimum number that we can tell me the configuration, right? Break things up. So this is this scenario. So be careful about the constraints, and we'll see more of that. So in this example, if you just had an airplane, an object that is suspended in the space, degree of freedom or DOF is 6. Depending on the constraint, so this part is fixed, So you only have 3, the rotation. But if you don't have any constant, you're going to get all of them. Now, for a coin on a paper. The coin has a face, right? So if you have a coin on a paper, you can get X and Y by where the coin is. But what if I rotate it, and that rotation, let's say there was a laser point here at his eye, okay? That will point somewhere. Is X and Y enough to tell me where the laser is going to point? No. What do you need? You need a third variable, so to tell the angle. So that's the degree of freedom. So on 2D, also on planar, you could have 2 or 3 degrees of freedom, or 1. Okay, so or 0 doesn't move. So you need to decide. So we have equations, but also intuition. When you look at a system, you can decide. Unless the system is too complicated, don't use the equations to tell us. Let's say you have a car. All right, same thing as the coin. You want to know where this car is. X, Y. So the X, Y of this is X and Y, but the car has a heading, right? And it happens that this heading is really important when you are trying to do the pathfinding. All right. So this is one of the variables that you are going to put on your equation and measure to decide about the location of your car. So that is one of the freedom. Now this car is in 3D space, right? It doesn't go up and down. It doesn't go right and left, but the motion, it does turn, has an X and Y. So that right and left could be go straight turn, creates that right and left.
So you're like programming.
Uh-huh.
And you want to turn it
Uh-huh.
at certain angle theta. Once you need to know how quickly it's going in that direction already,
Yes.
that'll vary how quickly.
Yes, so for cars, when you are trying to turn, how do you turn in your car? You change the velocity of the wheel, right? One turns faster, one turns slower, so one goes more, the other one goes less. You remember state space? X, Y, theta, X dot Y dot theta dot.
Yeah.
Right, so that goes to your program. So you have to have, so you give this space the velocity, that's the velocity, and then you can estimate the position from it, right? And that's the whole thing that you do, but that's the simple way. But basically that is the gist of autonomous navigation. Get the velocity. Now, how you get the velocity, that's the big question. And how, when you find a position, how do you evaluate if your position is where you actually want it to go? That's another topic. Make sense? But everything comes back to basics. So for this, that was a very good question. So if I wanted to write this space for this, X, Y, theta, let's say X1, Y1, Y2, theta 3, let's just follow our thing. And which X and Y are the roots, they're more complicated than just X and Y. Let's say X, Y, theta, and then X dot, Y dot, theta dot.
Would it be X21?
It's more complicated than that because you have the wheel encoders is not exactly X, Y. X, Y is calculated based on where the encoders are. Yeah.
So we have that like that theta because if it was like, for example, like a sphere,
Okay.
and it doesn't matter what.
So why is it different? But why? So very close is called heading. Why heading is important? Good question. It could be a sphere, but that exists and they're pretty cool. Why we care about the heading? Let's say it's a sphere, it doesn't matter. There's no front, right? If you want to think about it. But why does it matter? I would say there's still. It could be manipulated. What else? Like if the car has a camera and the camera always has to be in the front. If you are saying that, okay, I need to go to that corner, which is 30 degrees from where I started, you need to draw a line and then go 30 degrees from it to left, right? So you have to have a way to our next thing. Before that. So for degree of freedom, your rigid body freedom in that space, 2D or 3D, minus the number of constraints in that space will give you degree of freedom. Now look at your arm. There's a joint here, right? Pinch, you can tell. How many degrees of freedom my elbow has? 1. So what is the degree of freedom of my elbow as a rigid body in the space if it was just suspended? 6, because any rigid body in 3D space has 6 degrees of freedom. Now, how many constraints is applied to this? What direction it cannot move? In 5 directions. It only can move in 1. So this is basically the default. The default in 3D space is 6. So DOF is 6 minus, there are 5 directions I can't move my elbow. So it gives me 1. Exactly theta 1 degree of freedom. Now, let's say you have 2 bodies, you have an, so this is a prismatic joint, right? So it's a cylinder. You move only in 1 direction. This is in 3D space. So how many by default degree of freedom or rigid body freedom you have? 6. How many constraints are we applying in this? 5. It can only move in 1 direction. And you can see, it can't go this direction, up and down, and rotate, you're all velvet the ground. Make sense? So in your quiz, you're going to see questions that you're going to use this knowledge. So your quiz today has questions about everything that we taught, all right? Let's see. All right. Uh-huh. Uh-huh.
So it's pretty considered like a full degree.
It's 1 degree of freedom. It can rotate 0 to 90, 0 to 180, 0 to 270, depend on what you put in there. It's not about how much it goes, what is about what direction. Yeah.
You want to give
No. Yeah. Okay, we're so when your car has suspension, and good question, but if you're talking about navigation, moving from one place to another, once you're done, everything is back to home position, right? So you don't have any elevation. But if it's a forklift, you actually can go up and yes, you have another degree of freedom. But the suspension comes in play when you're calculating shocks and other things, vibration. So good question. I was just talking about a normal vehicle or car that you're just thinking about the navigation point. I will give you the password, but I want to know how far I'm going if I need to change the quiz. All right. Okay. Reference frame. Back to your question. How many of you have heard of reference frames? Hope everyone. The rest of you just don't want to raise your hand. But if you haven't, this is where we start to build the foundation. All right. So let's say I am standing here, which I am, and then Brett, if you wanted to say my position, let's say by just guess how many feet I am in X and Y. So this is, you're the point of reference. You want to say how many feet I am in your X axis and Y axis. Well, and then Alec, how about you? Okay, so every one of you is a different reference frame because you're seeing things from your point of view, your reference, and you see my position differently, right? You all give me a different point, even the two that are sitting next to each other, you still have the same. But I am here at the same spot. So reference frame is the point that we are measuring the position or velocity of an object from it. Now, hey, how about that you have a camera and he has a laser and I'm the object that you're trying to figure out the position. What are we going to do? Like every time we have to measure where this how far it is from us. Let's say now the camera is in your hand. So we need to find out where these reference frames are, and how they are connected. Once you know that, if I knew that all three of them can have information about my position, if one of them has information, because they know where they are with respect to each other, right? So from now on, whenever we talk about position of something, the velocity of something, it means that there was a reference point we measured with respect to that. And we're going to show it as subscript. So if you're in frame, I'm going to call you frame 0, you're frame 1. So my position P in frame 0, P0, is different from my position in frame 1, P1. I am in the same spot, right? So for all we care, we are going to only think about and work with inertial frame. Either I'm resting or I'm moving with constant, the frame. So the reference frame is either constant or moves with either fixed or moves with a constant velocity. So if a reference frame has acceleration, it will be not inertial, and in robotic, at least for our level, we don't care about it. So it's either fixed or constant velocity, which means acceleration is zero. Right? This makes things easier. Now, so back to state, position and velocity, we already talked about it. And we also can have, so these two create the steady state that we talked about. So we grab this position, right? And we grab this velocity. We say this is the state for the linear motion. Linear. And then we can also talk about orientation. We can say that here are the angular state of your object. All right. So orientation is you can't call any angles, theta, phi, zeta, whatever you call from the beginning, you always follow that. And then you will have a velocity, which is, so P is basically our theta off here. U is our x off here. Okay. So for an object, you might not have all of these in the state. So this is your big set. An object will have some of this, right? So if your theta is rotating along z-axis, and your object doesn't rotate along the other two axes, you only have theta and theta dot. So you don't have the other two states, for example, for revolution. So for this elbow, we can have all of this state, this body, but with this configuration, I can only have theta and theta dot. I don't have the other two. Okay. For prismatic joint, you could have x dot if you only move in one direction. The other two you don't have. But when we have a robot in general total, we can have all of those at some point. Because x is in x direction, y is in y direction, z in z direction. So you could have the translation in any of those directions. Make sense? We already talked about this. So if this is your frame 0, there's a point in frame 0, you have x. So if that is, I don't know, if you move this guy. Why did it is that little point in there? I don't know what's that. Okay, that's P0. X, P, Y, P, Z, P, U, V, W. And then if I have another reference frame, what is PB? If PA, if P in frame 0 is this, what is P in frame B? Look at the, so it's XB, YB, ZB, and then UB, VB, WB. Okay, same point, two different references. Okay. If it had orientation, we would add the orientation to it. I just put the position velocity in the linear aspect of it. You have access to all of the notes, so I'm going to just move. Coordinate system, you have planar and spatial Cartesian. You're familiar with this. You always have to know where your origin is. And then if this is P, you measure P with respect to the origin, right? What are the other coordinate frames? What are the other type of coordinate frames that we could have? Spherical, cylindrical, polar. In robotics, I think use polar and spherical a lot. But again, for this course, at least for the kinematic, you're just going to use Cartesian. Again, easier for us. Just makes our life easier. Because we're trying to learn fundamentals, so it's easy to start from simple. Now, I can give you the password, write it down, but I will need to give you 2 more slides at least, so you'll be able to do the quiz. So your password is Cool Beans. COOLBEANS. You access to this. Did everybody get that? Who watches Rick and Morty? It says always at the end. Do you get that? Oh, it's a better word. Listen soon. All right. What is a vector? What's a free vector? What's a vector? Part. It has magnitude and direction. So, does vector need to have a coordinate frame to be a vector? No. Let's say I'm moving in this direction. With a magnitude and with a direction, right? Now, from your point of view, I'm a different vector. From your point, I'm a different vector, right? But I'm still me. I'm a vector. I'm a free vector. So coordinate frame helps to define from their point of view. But nothing happens to the vector. It has direction and magnitude already. All right. Why is this important? Because we can trust and define different reference frames, measure a vector from those, and know that it's the same thing. So if we had a car, again, going in this direction, this was vector A, and then I have X, Y here, then A would be, let's say, A would be in this Cartesian X and Y. Okay. And if I had another frame here, X bar, Y bar, this was A, then I had X bar A, Y bar A. This was Y A, X A. So A here is X bar A, Y bar A. Right? Now, I have this vector, I measured this vector in 2 different reference frames. Right? So we talked about it, that's easy. How do I connect these 2 reference frames? How do I find the relation between them? Meaning that, how is XA and YA related to XB and YB? Oh, A, not B. I always mess up here. Okay. So that's this guy, this is this guy. What's this relationship? There's a transformation between this frame to this frame, right? So what happened to this frame that became that one? Just by observation. It rotated a little bit, right? And maybe moved in one direction. So there's a transformation, there's a mapping. If I can find that mapping and that translation transformation, okay, it seems like there's a rotation and a translation. If I find that, which is our rotation matrix is part of it, if I can find this, then any vector I have here, I can find same vector in the other one. So this is what we will discuss next week, Monday and Wednesday. All right. read the definitions of free vector that I wrote there before you take the quiz. All right. So I don't think I can do these two. Let's see. I probably need to change the quiz a little. Yeah, one question. So we finished up to here. I will post an annotated version. It has all of it. Okay. But on Monday we'll pick up from here. So things that you need to do is take quiz 1. You already gave the passport. Make sure you finish these ones. All right. All right. I'll see you on Monday. Sorry, let me pause this.